Welcome to Surveying and Geospatial Insights, the podcast that decodes the technology and practices shaping our world. I'm your host, Survey Steve. Today, we are tackling a technology that has fundamentally transformed our profession and is now a part of daily life for billions, the Global Navigation Satellite System, or GNSS. But as surveyors, we use it with a level of precision that is worlds away from the map on your smartphone. We're going to discuss GNSS accuracy and its many limitations. Joining me is Geomatics expert Deborah. Welcome.
It's a pleasure to be here, Steve. This topic is absolutely critical. GNSS is a phenomenal utility, but without a deep understanding of its error sources and limitations, it can be dangerously misleading. The difference between a 5-meter position and a 5-millimeter position lies entirely in understanding and mitigating these limitations.
Exactly. So today we'll start with the fundamentals of how GNSS works. Then we'll dive into the significant sources of error that we must contend with. Finally, and most importantly, we'll cover the techniques and best practices surveyors use to overcome these challenges and achieve survey-grade results.
Let's begin with the basics. Many people use the term GPS interchangeably with GNSS. While the American Global Positioning System, or GPS, was the first and is still the most well-known, GNSS is the more accurate generic term. It encompasses all satellite navigation constellations, including Russia's GLONASS, Europe's Galileo, and China's Beidou system. Modern survey-grade receivers are multi-constellation, tracking dozens of satellites simultaneously to improve availability and geometry.
The core principle behind it all is a concept called trilateration. Each satellite in orbit is broadcasting a very precise timing signal. A GNSS receiver on the ground picks up these signals, and measures the time it took for each signal to travel from the satellite to the receiver. Since the signal travels at the speed of light, this travel time can be converted into a distance, or a pseudo-range.
If you know your distance from one satellite, you know you are somewhere on the surface of a sphere with that radius, centered on the satellite. With a second satellite, you narrow your position down to the circle where the two spheres intersect. A third satellite narrows it down to just 2 points. And a fourth satellite resolves that ambiguity and, crucially, solves for the timing error in the receiver's less accurate clock. This basic, uncorrected measurement is what we call an autonomous position, and it's typically only accurate to within several meters.
Which brings us to the main event, the error budget. Why is an autonomous position off by several meters? It's because that simple time equals distance calculation is contaminated by a host of errors. We can categorize these into 3 main groups: satellite-based errors, atmospheric errors, and receiver-based errors.
Let's start with the satellites themselves. Although they carry incredibly precise atomic clocks, they aren't perfect and can have minuscule clock drifts. There are also ephemeris errors, which are slight deviations in the satellite's actual orbit compared to its predicted broadcast orbit. These errors introduce a meter or two of uncertainty, but thankfully, they are closely monitored and corrected. Data is included in the broadcast navigation message, significantly reducing their impact.
The next and largest source of error is the Earth's atmosphere. As the GNSS signal travels over 20,000 kilometers through space, its last few hundred kilometers through our atmosphere cause major problems. First, it hits the ionosphere, a layer of charged particles from about 80 to 600 kilometers up. This layer slows and refracts the signal, potentially introducing many meters of range error. The effect is most pronounced during periods of high solar activity.
After the ionosphere, the signal must pass through the troposphere, the lower, denser part of the atmosphere where we live and where our weather occurs. Changes in temperature, pressure, and especially humidity affect the signal speed, causing a tropospheric delay. This delay is particularly difficult to model accurately because it is so variable over short distances and times. This can add another meter or more of error.
Finally, we have receiver-based errors, which occur in the immediate vicinity of the antenna. The most notorious of these is multipath. This happens when the satellite signal doesn't just arrive via a direct line-of-sight path, but also bounces off nearby reflective surfaces, like buildings, vehicles, water, or even the ground itself. These reflected signals travel a longer path, arrive at the antenna slightly delayed, and corrupt the true signal, leading to significant position errors.
So, With this daunting list of errors, how do surveyors achieve the incredible precision our work demands? The answer lies in a technique called differential positioning. Instead of one receiver working in isolation, we use two or more. The most common method for surveyors is real-time kinematic, or RTK.
RTK requires two receivers operating simultaneously, a base and a rover. The base station is set up over a point with known coordinates. Because it knows precisely where it is, it can calculate the error in the satellite signals it is receiving at any given moment. It then broadcasts this error information as a correction message to the rover via a radio or cellular data link.
The fundamental assumption of RTK is that because the base and rover are relatively close to each other, say within 10 to 20 kilometers, they are seeing the exact same satellite and atmospheric errors. By applying the correction message from the base, the rover can effectively cancel out these common errors from its own measurements, allowing it to calculate its position with centimeter-level accuracy in real time.
For situations where a real-time data link isn't feasible, we can use post-processed kinematic, or PPK. The principle is the same, but instead of transmitting corrections in real time, both the base and rover simply log their raw satellite observations. Later, back in the office, specialized software combines these two data files. It can analyze the data forwards and backwards in time to resolve ambiguities, often resulting in an even more robust and precise solution than RTK.
An increasingly popular evolution of this is network RTK. Instead of using a single base station, it utilizes a whole network of continuously operating reference stations, or cores. These networks model the atmospheric errors over a wide geographic area. When a surveyor connects their rover to the network, they receive a localized correction that is customized for their specific position, as if a virtual reference station was set up right next to them. This eliminates the need for the surveyor to maintain their own base station, increasing efficiency dramatically.
And that convenience is a game changer. But it's also important to understand that not all networks are created equal. The density of the core stations, the quality of the software, and the latency of the data link all play a role in the final accuracy and reliability a user can achieve.
Even with RTK or network RTK, the solution is not instantaneous. When you first start a measurement on a new point, the receiver's algorithm needs time to resolve what's called the integer ambiguity. This is the process of determining the exact whole number of carrier wave cycles between each satellite and the antenna. An RTK fixed solution means it has successfully resolved these ambiguities, providing the highest level of precision. A float solution means it has a good approximate position, but hasn't achieved that final lock. An ethical surveyor never records a float position for a final coordinate.
Understanding the theory is one thing, but applying it in the field requires a strict adherence to best practices. This starts before you ever leave the office, with mission planning. A professional surveyor will use software to predict the satellite availability and geometry for their project location and time.
Another critical aspect of mission planning that has become more important with the modernization of GNSS is accounting for different constellations. A surveyor needs to ensure their receiver firmware is up to date to track all available signals, and their software can process them correctly. Relying on GPS alone is a thing of the past. A modern surveyor leverages every satellite in the sky to their advantage. This also means understanding that different constellations have different reference frames, and ensuring your software correctly handles the transformations between them to maintain geodetic integrity. It adds a layer of complexity, but the payoff in terms of availability and reliability, especially in challenging environments, is enormous. Absolutely. The key metric we look for is the position dilution of precision, or PDOP. This number represents the quality of the satellite geometry. A low PDOP value, ideally under 2, indicates that the satellites are spread out well across the sky, providing a strong geometric solution. A high PDOP means the satellites are bunched together, leading to a weak geometry and a magnified error in the final position. We plan our observations to avoid these periods of high PDOP.
On-site, meticulous procedure is key. When setting up a base station, select a location with a completely unobstructed view of the sky and far away from any potential multipath sources. Use a fixed-height tripod to eliminate the possibility of human error in measuring the antenna height, and ensure the base is collecting data for the entire duration of the survey.
As for the rover, the surveyor must always be aware of their surroundings. You cannot get a reliable measurement under a dense tree canopy, next to a tall building, or near a chain-link fence. It's also vital to trust, but verify the information on your data collector. Don't just accept a fixed RTK solution. A good practitioner checks the quality indicators, the residuals, and performs redundant measurements. A cardinal rule of all surveying is to check your work, and GNSS is no exception. This means beginning and ending every session by measuring into known control points to verify that your entire system is performing as expected.
Those are excellent points about field procedures, Deborah, and they highlight another layer of complexity that is absolutely crucial for surveyors: the geodetic datum. It's a topic that's often invisible to the casual user, but for us, it's the very foundation upon which all our coordinates are built. Getting the measurement right is only half the battle. You have to know what you're measuring it in reference to.
You're absolutely right, Steve. A geodetic datum is essentially the reference frame for all our coordinates. It's a complex model of the Earth that includes an origin point, orientation, and a mathematical surface, or ellipsoid, that approximates the Earth's shape. When your GNSS receiver gives you a latitude and longitude, that position is only meaningful in the context of the specific datum it's using, like WGS-84, which is the native datum for the GPS constellation.
And that's a critical distinction. While a smartphone user is perfectly happy with a WGS-84 position that's consistent globally, a surveyor's work must be referenced to a local or national datum, like N8083 in North America. The coordinates can differ by a meter or more between these datums. A surveyor who fails to correctly apply the transformation from the satellite's datum to the project's required datum is introducing a massive blunder before a single measurement is even considered.
Precisely, and it gets even more complicated. Most construction plans and legal documents aren't based on latitude and longitude on a curved ellipsoid. They're on a flat plane using a map projection like the State Plane Coordinate System, or UT. So, the surveyor must not only handle the datum transformation, but also correctly apply the projection, accounting for scale factors and convergence angles. Each step is a potential source of significant error if not handled with expertise. It's a key part of what separates a professional from a technician.
This also brings up the issue of vertical datums. GNSS natively measures heights above the mathematical ellipsoid, which are not the same as the orthometric heights or elevations above mean sea level that we need for engineering and construction. Bridging this gap requires the use of a geoid model, which is another complex surface that models the difference between the ellipsoid and mean sea level. Using the wrong geoid model can introduce vertical errors of several feet.
And these models are constantly being updated. The National Geodetic Survey is preparing to release a new, more accurate gravimetric geoid model in the coming years, which will obsolete much of the existing vertical data. A competent surveyor must stay abreast of these changes, understand their implications for legacy projects, and be prepared to educate their clients. It's a continuous process of learning and adaptation.
That's a perfect example of the continuous professional development required in our field. It also highlights the absolute necessity of independent checks and redundancy. It's not enough to just occupy a point once. A rigorous survey will involve multiple observations, on different days if possible, using different equipment or even different techniques, like combining GNSS with a total station traverse, to ensure the highest confidence in the results.
Exactly. That principle of trust but verify is paramount. Every measurement has a story to tell, and that story includes its quality, its uncertainties, and its context. A professional surveyor doesn't just deliver coordinates, they deliver a complete, defensible measurement record. This meticulous approach is what separates a high-quality geodetic survey from just a collection of points.
To bring it all together, GNSS is a revolutionary technology that has granted us unprecedented positioning capabilities. But it is not an infallible black box. The path from meter-level uncertainty to millimeter-level precision is paved with a deep understanding of the physics, a healthy respect for the error sources, and an unwavering commitment to professional best practices.
That's the perfect summation, Steve. It's our knowledge and methodology that transform this global utility into a true surveying instrument. Thank you for having me on to discuss it.
Thank you, Deborah, and thanks to all of you for listening to Surveying and Geospatial Insights. Join us next time for another in-depth look at the world of measurement.